So next up we have what we call the sequential criterion for functional limits. And this is actually going to provide a method for us to show when limits don't exist, which if you have to rely on the definition for that, that can be a really kind of difficult thing to have to show. So the sequential criterion for functional limits is going to be kind of our main result that we'll use when we have to show that a limit doesn't exist. Now we'll talk about exactly how that works after we prove at least one direction for the theorem. I think the second direction I'll just refer you to the text because it's the first direction that we're actually going to use in our test for limits that don't exist. All right, so what does the theorem say? It says that if the limit as x goes to c of f of x is equal to some real number L, well, that happens if and only if every sequence, for every sequence that converges to c, the function values converge to L. So this is a way of expressing that a limit exists using sequences that are approaching C. Now, I think the statement looks a little bit more complicated than the idea. So here's the idea of the theorem. I've pictured here a function whose limit exists, right, as x gets close to C, then f of x gets close to L. I've left a hole over where f of c would be just to remind us that c doesn't have to be in the domain of the function. So this isn't necessarily a continuous function or even defined at c. Now what the sequential criterion says is that if I came along and took a sequence that's converging to c, right, so the points in my sequence get closer and closer to c, well then it must be the case that if I take the function evaluated at those points, the function values of the sequence get closer and closer to L. So it's kind of, we're just taking particular points that are getting close to C as opposed to the definition of the limit, which is thinking about all possible points that are within, say, delta of C. All right, so let's take a look at what the proof is going to be. Similar structure to our previous proofs. We're going to start off just proving the forward direction. So we assume that we have a functional limit, and we want to show that the function values for every sequence converging to C have the same limit. All right, so assume that the limit of the function is L, and let's suppose that we've got some sequence converging to C. We are always careful to rule out the value C itself because that's not a concern of the limit definition. And then we take some epsilon bigger than 0, and note that what we want to make small is this f of xn minus L. So what we want is the usual thing. Can we make that quantity smaller than epsilon? Well, remember that this f of xn is a sequence itself. And so what that means is we need to find capital N such that n bigger than capital N implies that f of xn is within epsilon of capital L. Well, we know already that we have a functional limit equal to L. So what that tells us is the following. Since the limit x approaches c of f of x is equal to L, there exists some delta such that if x is within c of delta, f of x minus L is f of x minus L is smaller than epsilon. Well, now we use the fact that x sub n is a sequence converging to C to take n large enough that this inequality is satisfied. Right? So since xn converges to C, there exists a capital N such that if I am far enough out in the sequence, I can make xn minus C be less than delta. And basically that completes the proof. We just have to put it together. So for epsilon bigger than 0, take n as above, and n bigger than capital N implies that xn minus C is less than delta. And by the definition of our functional limit and the way delta was selected, that implies that f of xn minus L is less than epsilon, because x sub n is one of these x's that's within delta of C. So that completes the proof. One little detail to clear up, in the definition of functional limit, right, this greater than 0 rules out x being C. And while I haven't specified it here, remember that xn is a sequence that's approaching C but doesn't equal C. So that's actually kind of implied in how we constructed our sequence, but we could also have been a little bit more explicit, included the greater than 0 there, but it's not really required for the way we structured the proof.